In the vast expanse of the universe and within the intricate microcosms of atomic particles, the captivating allure of perpetual motion has beckoned scientists and philosophers alike through the millennia. Imagine a world where machines run indefinitely without the need for external energy, a realm where the ceaseless motion of planets and atoms manifests the dream of eternal movement. This enchanting vision, however, treads the blurry line between the achievable and the realm of scientific impossibility, guided by the unyielding laws of thermodynamics. But what if the secrets of perpetual motion could unlock new dimensions of understanding within physics, challenging our perspectives on energy, entropy, and the very fabric of reality? The notion of perpetual motion is not merely a scientific query, but a profound human aspiration that mirrors our deepest desires for independence and sustainability. This quest, historically peppered with both ingenious designs and fanciful errors, serves as a fertile ground for exploring fundamental physics concepts through the ages. The allure of machines promising endless power without fuel has historically attracted brilliant minds and charlatans alike, each contributing uniquely to this captivating scientific narrative. These endeavors, though misguided in their ultimate goal, have inadvertently propelled the understanding of energy systems forward, shedding light on the intricate dance between forces, motion, and the laws governing them. Yet despite centuries of innovation, the reality remains that true perpetual motion machines are not just impractical, but theoretically impossible as posited by the laws of thermodynamics. This fundamental constraint frames the context in which we explore seeming perpetual phenomena in nature. The first law of thermodynamics, also known as the law of energy conservation, states that energy within a closed system must remain constant. It cannot be created nor destroyed, only transformed. In the context of perpetual motion, this law implies that a machine which produces more energy than it consumes, a so-called over-unity device, cannot exist. Understanding this energy flow within isolated systems reveals why perpetual motion machines on a macroscopic scale defy this fundamental law. Every attempt at creating such devices invariably results in a net loss of energy, typically through unaccounted forces like friction or thermal dissipation. This understanding does not dampen the intrigue of perpetual motion, but redirects it toward more scientifically salient discussions about efficiency and energy transformation in natural and engineered systems. Central to the impossibility of perpetual motion machines is the second law of thermodynamics, which deals with the concept of entropy, a measure of disorder or randomness in a system. This law states that in any closed system, entropy tends to increase over time, leading inevitably to a state of maximum entropy and minimal energy availability. This unavoidable increase in entropy is the arch-nemesis of perpetual motion machines. It dictates that without an external input of energy, no system can continue its function indefinitely. Each motion, no matter how small, contributes to the overall entropy of the system, gradually sapping it of usable energy. This law not only rules out the possibility of traditional perpetual motion, but also deepens our understanding of the universal tendency towards disorder, a fundamental concept that underscores the transient nature of all motion in the universe. Brownian motion, the dance of randomness. Brownian motion serves as an enchanting illustration of perpetual-like movement within the microscopic world. Observed first by Robert Brown in 1827, this phenomenon involves the erratic, continuous movement of microscopic particles, suspended in a fluid, driven by the unceasing collision with molecules of the fluid. These particles jiggle endlessly, driven by the kinetic energy of the surrounding fluid molecules. At a glance, this motion might seem to offer a loophole to perpetual motion. However, it's crucial to understand that this energy is not generated from within the system but transferred from the thermal energy of the fluid, which itself is derived from the environment. This microscopic dance, while ceaselessly dynamic, aligns perfectly with the principles of thermodynamics, revealing the complex interactions between energy transfer, particle dynamics, and environmental influences in seemingly isolated systems. Electrons in atoms, an endless waltz? In the atomic realm, electrons orbiting the nucleus appear to engage in a perpetual dance. This motion, fundamental to chemical bonding and the properties of matter, challenges our macroscopic understanding of movement and energy. Contrary to classical mechanics, quantum mechanics reveals that these electrons are not consuming energy as they orbit. Instead, they exist in stable quantum states or orbitals, where no net energy is exchanged. This stability arises from the quantum mechanical nature of electrons, which prevents them from spiraling into the nucleus or radiating energy as classical charged particles would. Thus, while electrons exhibit ceaseless motion, they do not violate thermodynamic laws. Instead, they highlight the unique rules governing subatomic particles, rules that differ markedly from our everyday experiences with motion and energy. Planetary orbits, the timeless ballet. The motion of planets around stars, moons around planets, and the myriad of celestial bodies participating in the cosmic dance offers a macroscopic parallel to the atomic orbits. Governed by gravitational forces, these orbits can persist for billions of years, emblematic of the closest real-world approximation to perpetual motion. This enduring motion is sustained by the gravitational wells created by celestial bodies, within which the planets travel. Energy losses through mechanisms like gravitational radiation are so minuscule that they become significant only over astronomical timescales. Here, the laws of celestial mechanics ensure conservation of angular momentum and energy, keeping the planets in their paths without external energy input. Again, while planetary orbits may suggest a kind of perpetual motion, they adhere strictly to the conservation laws set out by physics, showcasing a grand-scale interplay of forces that sustains movement over cosmic timescales. Venturing deeper into theoretical physics, the concept of the quantum vacuum presents a landscape teeming with activity. Contrary to being a simple void, the quantum vacuum is a state of lowest possible energy, filled with fleeting particles and antiparticles that continuously appear and vanish. These vacuum fluctuations are spontaneous and inherently unpredictable, driven by the principles of quantum mechanics. They provide a theoretical groundwork for understanding how even nothing is never truly inert or static at the quantum level. While this phenomenon suggests a universe bubbling with perpetual activity, it is governed by the uncertainty principle and does not lead to macroscopic perpetual motion or usable energy output, again illustrating the constraints imposed by fundamental physical laws. Throughout history, the pursuit of macroscopic perpetual motion machines has captivated inventors from Leonardo da Vinci to modern-day enthusiasts. These machines, designed to operate indefinitely without an energy source, have ranged from overbalanced wheels to magnet-driven devices. Each invention, though failing to achieve perpetual motion, has contributed to a deeper understanding of mechanical principles and the insurmountable nature of energy losses through friction and other forces. This historical journey through perpetual motion attempts not only highlights human ingenuity and persistence, but also the relentless pursuit of understanding the boundaries set by the natural laws of physics. Conservation laws play a pivotal role in the scientific dissection of perpetual motion theories. These laws, which include the conservation of energy, momentum, and angular momentum, serve as the bedrock principles governing all physical processes. They dictate that in a closed system certain quantities remain constant unless acted upon by external forces. In every proposed perpetual motion scenario, whether it be a mechanical device or a natural phenomenon like the motion of celestial bodies, it is these conservation laws that provide the ultimate test. For instance, a device that supposedly generates more energy than it consumes would violate the conservation of energy, making it scientifically implausible. Understanding these laws not only helps debunk unfeasible perpetual motion machines, but also enriches our comprehension of how real systems evolve and interact, maintaining a balance dictated by these fundamental principles. While true perpetual motion remains an unattainable ideal, theoretical physics continues to push the boundaries of what might be possible. Concepts such as time crystals, first proposed in 2012, represent structures that repeat in time as well as in space, suggesting a form of motion that could theoretically persist in a ground state without energy input. These theoretical constructs, while not perpetual motion machines in the traditional sense, challenge our understanding of dynamic systems and offer fascinating glimpses into potential new states of matter. They underscore the creative and often unexpected ways in which the laws of physics manifest, opening doors to novel technologies and deeper understanding of the universe. This exploration of theoretical physics does not seek to contravene established laws, but to expand our perspective on how these laws can be manifested in extraordinary conditions. The concept of perpetual motion is not confined to physics alone, but extends into the realm of biological systems. For instance, the continuous movement of ions across cellular membranes is critical for life, and while it may appear as a form of perpetual motion, it is driven by metabolic energy derived from food or sunlight. Biological systems with their complex feedback and regulatory mechanisms illustrate a form of sustained motion that is energetically and thermodynamically balanced. This interplay between biological function and thermodynamic principles provides a compelling narrative on how life maneuvers within the constraints of physical laws, perpetuating motion in a way that is sustainable rather than perpetual. The pursuit of perpetual motion while grounded in the impossible has yielded substantial scientific and technological advancements. This quest, driven by human curiosity and the desire for infinite sustainability, has deepened our understanding of the fundamental laws of physics and pushed the boundaries of energy, efficiency, and conservation. The lessons learned from exploring the boundaries of perpetual motion are manifold. They remind us of the limitations imposed by the natural laws, the importance of energy efficiency, and the potential of exploring theoretical realms that may seem counterintuitive. As we continue to advance technologically and scientifically, the narrative of perpetual motion serves as both a cautionary tale and a beacon of inspiration, encouraging us to think creatively within the framework of what is known and to explore responsibly the realms of what might be possible.